Darren Grant joined the MSU Department of Physics and Astronomy in the fall of 2018, so he's a very new Spartan. We recruited him away from the University of Alberta as a new hire under the Global Impact Initiative. Professor Grant earned his PhD in physics, specializing in particle physics from Carleton University in Ottawa, and later conducted postdoctoral research at Case Western Reserve University and Penn State before moving to Alberta as a faculty member. He has made a career of studying the properties of some of nature's most elusive fundamental particles through the development of ultra-sensitive detectors deployed in extreme locations around the globe. An example of these elusive particles is the neutrino, which all of you know is produced copiously in the nuclear reactions, for example, in the sun. There are about 1 billion neutrinos passing through, many billions of neutrinos passing through every cubic centimeter of your body at this very moment. But they interact so weakly with us that you don't feel them. And so because they interact so weakly, it takes extraordinary measures to capture and detect these neutrinos, which Darren will tell you about. A recent recipient of the Natural Sciences and Engineering Research Council of Canada's Stacey Memorial Fellowship and an elected member of the College of the Royal Society of Canada, Darren is currently the spokesperson, one of the leaders, for the IceCube Neutrino Observatory in Antarctica, which is actually pictured there on the screen. Commonly referred to as IceCube, the observatory is the world's premier experiment for the study of high-energy neutrinos originating from the most powerful astrophysical processes, and it has begun to reshape how we view our universe. The title of his presentation today is Neutrino Hunting in the Antarctic. No, that is not a title of an X-Files show. It is not science fiction, and he will tell us all about it. Thank you, Darren.
Thank you, Steve. President of the members of the Board of Trustees, thank you so much for the opportunity to speak with you today. It's an incredible pleasure to be here. I wasn't sure I was going to make it, and so all the better this morning. My talk today is titled Neutrino Hunting in the Antarctic. What you see on the screen at the moment is the IceCube Laboratory. This is not IceCube in itself, as you'll see in the coming slides. And that bright object in the top right, this will become clear at the end of my talk. This is one of the most exciting things that I think has happened in the field in the last year or in the last few years. So I'll begin. I'll keep this simple. If everything that you see around you is beautifully summarized in the circle that you see here. There are 12 particles that make up our universe, and then there are force carriers. What my talk is about is in the bottom right. It's a cornerstone of what we call the standard model. These are the neutrinos. They are called nature's ghosts. This is a nickname that came to them shortly after they were first postulated in the 1930s. And they're called that, as Steve mentioned, because if you look at your thumbnail, it's about a square centimeter in size. There's on the order of 10 billion neutrinos passing through that thumbnail every second. They continue through your body, and they continue to the far edges of the universe. This is how they behave, which makes them incredibly challenging to study. And for this, you have to instrument enormous detectors. It also makes it very rewarding. In the last 60 years, there have been 4 Nobel Prizes to date in the study of the neutrino properties, about every 10 to 15 years in time. And in the time that I've discussed this slide, 3 trillion neutrinos have now passed through your body. So we have constructed the world's largest neutrino detector. It is called the IceCube Neutrino Observatory. What you see here is South Pole Station, Antarctica. That is marked as the living quarters in the image. The IceCube lab that you saw in the very first slide is shown on the far right of the image. And just for scale, you can see a skiway, which is where a Hercules C-130 aircraft lands with people and equipment during the summer period. And the outline is what you have for the IceCube Neutrino Observatory. Now, the heart of the observatory is in the deep ice. In the small object, dark object that you can see, that is the Eiffel Tower. For scale, we choose the Eiffel Tower because we have no French collaborators. It makes it easy to choose the object. We completed this detector late in 2010, and it has been operating with nearly 100% efficiency over the last decade. What we have done is instrumented a cubic kilometer of the extremely pure, transparent polar ice, a kilometer and a half deep, up to 2.5 kilometers into the deep glacier near the barbershop pole that you can see in the top image. Now, this is what happens to the landscape when we're busy. What you see in the top left corner is our drill facility. We have 5 megawatts of power burning jet fuel to produce hot water. We melt our way into the glacier. And once we do that, the hole that we create stays liquid for 24 hours. During that time, we deploy the sensors that you see in the bottom images. These are sensors that we're starting to lead in the development of here at Michigan State University for the next step of the detector. And so what you have is a distributed grid of very sensitive light sensors. Now, these sensors, I'll give you an example. They're the inverse of a light bulb. What happens is they look for light that's produced in the very deep ice when a particle interacts. If I hand you a match and I send you to a mountain that I was recently on, and I take that sensor to the moon and you light that match, you will see that light with this sensor. That's how sensitive they are once we deploy them in the deep glacier. Now, we explore the universe through neutrinos with these detectors. And once IceCube opened for business in 2010, the world started to take notice with major press headlines in the Washington Post and the New York Times. 2 years later, we started to see the very first astrophysical neutrinos from the farthest reaches of the universe. And these were covered in major press events. We were awarded the Breakthrough of the Year in 2013 for this. Our first 2 events were some of the highest energy particles ever measured, and we named them Bert and Ernie. And so this is Ernie. This is what you see in our detector when an event goes off. It's a beautifully simplistic detector. When you see light, one of our sensors lights up. That's the ball that you see on the screen. It's an enormous detector. If I take Ernie and I bring him to Michigan State University, this is what he looks like. He would basically fill the entire campus from top to bottom. And most recently, this is incredibly exciting. It's what we announced last year. What you see here is a neutrino event which has left this beautiful long track in the detector. Now, with that track, you are able to point back into the universe to look at where this neutrino came from. And if I follow that line back 4 billion light years to the shoulder of Orion in our night sky, you will find a blazar. And that is the first correlation ever of a high-energy neutrino from one of the most extreme astrophysical events in the universe. We announced this to the world. The world followed this up with over 20 observatories around the globe and in space, and they also saw this blazar in a heightened peak of activity. Oops. The world took notice. We got the cover of Science. That was fantastic. Press impacts over 20,000 articles, videos, radio, podcasts through all major news facilities occurred, 39 countries on 7 continents, including Antarctica. They took notice. I picked one of my favorite headlines from Vox, 10 science stories that made us go, whoa, that's awesome. And this is where we are today. This is what we want to accomplish here at Michigan State, leading this international team of scientists. I draw on 2 sources of inspiration. We call this the Generation 2 or Gen 2 detector. Those are the penguins that you see in the top right corner. My other source of inspiration comes from Mick Jagger. Anything worth doing is worth overdoing. What we want to do is construct on the order of a $300 million extension to the IceCube Neutrino Observatory through this Generation 2 detector. We have been approved full funding now for the first phase of this upgrade, and we are taking leadership in this at Michigan State University through major elements of this project. So I will close with these beautiful windows. For 400 years, we have studied the universe through electromagnetic radiation, through the full spectrum of what we can see in light. 2 years ago, we had gravitational waves measured in coincidence with astrophysical activities, extreme events in the universe, and now neutrinos have joined that landscape for our windows to the universe. I thank you for your attention. This is our team at Michigan State University. It's growing quickly, and then our collaboration. Thank you.
As the audience ombudsman, I just want you to define blazar for everybody.
Sorry. So a blazar is a supermassive black hole. It's at the center of a galaxy. And so what happens is it accretes matter from that galaxy. When it does this, it emits an extremely powerful jet. When that jet is pointed towards the Earth, that's when you call it a blazar.
And on the record, you're going to tell us for sure there's no flying saucer under that ice. You're really just studying neutrinos.
Right. So we've discovered ham from the 1970s, but no UFOs.
Okay.
So when is this expansion effort going to start?
So we're already starting to build for the phase 1 upgrade for the first step in that detector. The deployment for that is expected in 2022, and then we're optimistic that funding will be positive and that we would move forward with the full Generation 2 detector shortly thereafter.
I also want to add that one of the Nobel Prize winners that you talked about is going to be visiting this campus one of these days. So
yes,
that's another.
Yeah.
That's another. Any questions?
I wanted to offer that when we learned about the IceCube during our orientation, Trustee T-Bay said she would like to be the first trustee to go and visit the IceCube. So just letting you know that.
Go in the summer, though.
You want to stand behind me.
Right. You all are doing some great work, so thank you for that.
Thank you.
Thank you. Thank you so much.